everyone, welcome back to Comp 2160 Programming Practices. This is a little bit of a different lecture in that we're kind of doing this asynchronously. I am out on a field trip today, and I just want to make sure that we are keeping on with this course. So today in this lecture, what I want you to be able to do is I want you to be able to define the pre and post conditions for a routine. Routine here is kind of a fancy word for a block or a function. That's really what this is. It's just a fancy word for a block or a function. Pre and post conditions are going to be assumptions that we have about the state of things as we go into or come out of a function or a block, but we'll take a look at that in a little bit. I want you to be able to define the invariants that encapsulate the valid states of an abstract data type. And I want you to be able to use preconditions, postconditions, and invariants to validate the runtime behavior of an ADT being used in an application. This is all about design by contract. All three of these are under this major big heading that's called design by contract. And what we're going to see really shortly is that these are all quite fancy ways to say we are making assumptions about things in terms of the inputs and outputs for a function or a block of code that we've got, but we've never written those things down. And design by contract is very much about writing those things down and then verifying that that's actually what the state of things is in the code that we're looking at right now. So let's get started. Design by contract is a tool to prevent programming errors. This is not language specific stuff. So everything that we're looking at in terms of design by contract is something that you can do in every programming language that you have access to. In fact, in Java, you've kind of already done a little bit of design by contract in the form of those assert statements in assignment 1. This is not language specific. This has nothing to do with C. We're going to implement this in C, and this is not a C course. C is a means to an end. We're going to use C to implement these ideas, but this is something that you can do in all the programming languages that you're working with. This is also not a tool for preventing user errors. The people that are going to eventually use the software that we're writing are the users that we've got, but this is not a tool for preventing them getting into bad states with the code that we've written, but instead this is a way for us to help us. So I am a programmer here, I'm a computer scientist, you are a programmer, you are a computer scientist. This is really about making sure that you're able to get something out of the code that you've written in terms of meaningful error messages and preventing getting into an exceptional state in the first place. So this is code that you write that encodes your assumptions about the inputs, outputs, and states of the program that you are writing. So programming errors. What kinds of programming errors can a programmer write? What kinds of programming errors can a programmer write? Syntax errors, you forget to put a semicolon in, you use the wrong name for an identifier, you mistype a variable name. These are syntax errors, and these are really going to be handled by the compiler. There are times where you forget to check some of the inputs that you've got. So if you're writing in a programming language like Python or JavaScript, Python and JavaScript don't have types attached to their data. And so if you don't check that the type of data that you're expecting to get from a function is what you're assuming it's going to be, this is the kind of a programming error that you as a programmer can write. It's also going to be things like checking for null. So we are very familiar with null pointer exception. If we don't check for a null pointer before we try to use it, it's going to give us a null pointer exception. And then the one that we've most commonly seen, and I kind of remember back to one of the earlier lectures that we had in this term where I was asking you about the kinds of errors and exceptions that you most often see. More people said this than null pointer exception, which honestly I was kind of surprised about, but that is what it is. These are the kinds of programming errors that a programmer can write. You can make code that will go out of the bounds of an array. This is not the kind of error that your parents are going to encounter when they're using the code that you've written. Design by contract is exception prevention. So remember that C does not have exceptions. We've now spent quite a lot of time with C, and we've run into at least a few places where C not having array index at a bounds exception kind of bites us. It just goes past the end of the array and doesn't ask any questions about it. Design by contract is a tool that's intended to prevent exceptional behavior during development. So it's a tool to help you identify exceptional behavior while you're writing your code. It's not really intended to help you after you've given your code to someone, but it's trying to make sure that you are identifying all these exceptional states before you give your code to someone. So how do we prevent exceptions? And to answer that question, we kind of have to answer this question, what even is an exception? An exception is something that happens while your program is running where it can't or shouldn't proceed. So what do I mean by can't or shouldn't proceed? One example of this is you've got a null pointer. And note here that I've got null with lowercase null, a null pointer. When you are running Java code and you've got a variable that has a value of null, and you get a null pointer exception, your program and the JVM immediately halt execution. It cannot go on. It can't continue because it doesn't really make sense for it to continue. What is it supposed to do after it gets this null pointer exception on the class or on the variable that you're looking at? This can be file related issues. So if you write code that is intended to read a file, but you get this file not found exception, it kind of has to stop. It cannot continue. The way that it continues is you catch that exception and you pop up an error message that says choose a different file, but really the code that you've written cannot continue to execute. Division by zero is an arithmetic exception in Java. When you divide by zero, your code can't or shouldn't continue. And then this is the one that we see most often, array index out of bounds exception. So when we get index or bounds errors in Java, our code just stops. In C, we've been seeing that it just keeps going, but in Java, it just stops. Everything completely stops and we don't continue executing code. All of those exceptions are coming from violations of the assumptions that we have about the code that we've written, usually. There are 3 places that we have assumptions about things and 3 places that those assumptions can be violated. One is before we start processing data, and this is at the beginning of a block. It can be after we finish processing data, and this is at the end of a block. Or it can be the state of an object. So the state of an instance of a class or the state of just a thing that we've got. It might be just one single variable, one single primitive variable type, but it's going to be something, the state of something that we have through execution. Let's take a look at some code snippets, and these code snippets are going to be ones that we've seen in class. So they're not really new code snippets, but I want to take a look at these ones in particular. Let's take a look at some code snippets, and then we're going to come up with or describe some assumptions about the inputs and outputs of those code snippets. Here's a function that we wrote in class, just the last lecture that we had. We've got this make string. This is our constructor function, and it takes 2 arguments, an array of characters and an integer that's called numchars. And this function returns a pointer to a string object. This is that struct string that we defined. We've got 2 inputs, and we're making some assumptions about those inputs. One is that numchars is greater than or equal to 0. So we're taking an array of characters as input. We're treating that array of characters as a string in C. We're passing this in as an array, and so we are accepting the number of characters or the number of elements of that array that we want to work with. We are making an assumption that numchars is greater than or equal to 0. We're making an assumption that characters is not equal to uppercase NULL, because now we're thinking about C. We're making an assumption that characters is not null. So now I'm going to ask this question: can characters equal null? And the answer is yes, it can. And this is actually related to this idea that when we're looking at functions, arrays and pointers can kind of be interchangeable. We are making this assumption that characters cannot be equal to null. We're making this assumption that characters is a valid C string that has that null byte at the end of the string. Characters at numchars is equal to the null byte. These are the input assumptions that we're making about our inputs for this code. We're also making some assumptions about the outputs that we are giving. So we're writing that makeString function. We're making some assumptions about the outputs. The main thing is that we're returning a valid string struct. We're assuming that when we pass this valid string struct back, that the contents of that string are equal to what was passed into us. So whatever we are internally representing as a string type, we're assuming that whatever our internal representation, that private internal implementation has, the contents of what we have in that string struct are equal to characters. We're also making an assumption that that null byte is in the right place. So we've put that null byte into the correct location in the string, the array of characters that we've got. We're also assuming that the length, so this is specifically about struct string, we're assuming that the length is greater than or equal to 0, and that the at length is where the null byte is. Another function that we wrote in class is this char_at function. The input assumptions here for char_at were that index is greater than or equal to 0. Index is less than the length of the string. This is an assumption that we're making. My string is a valid instance of this string structure. And then the output assumptions that we're making are that the character that we return is actually in the string. So if we were to look in the string data that we've got inside the string object for the character that we're returning, we should find it. Or we're returning a null byte because the input assumptions were violated. So that index is less than 0, or it's going to be greater than the length of the string. And the other output assumption that we're making is that the string that we originally had has not been modified in this code. Some of these assumptions that we're making here for both makeString, so let me go back here, the input assumptions that we're making for makeString and the input assumptions that we're making for char_at, these are things that I have written into the comments for these functions. So if you look at the interface that we defined for char_at and makeString, these comments, with the exception of the valid struct string thing, these are things that I wrote into comments about the assumptions. These are assumptions that we have. They may seem obvious to us as the person that's writing this code, but they are assumptions that we have. These are part of the contract that we're defining. This is another piece of code. This is an example of where we have an assumption about the state of a value as code is running. Assumptions can also happen in a non-function block. All the things that we looked at as inputs and outputs are in the context of a function. Assumptions can also happen in a non-function block. We can also have assumptions about values inside this loop. Let's take a look at this code in action. So for some reference, this code looks like pretty reasonable code. This is a small fragment of code that that I was working through with a student a couple of years ago, where at first glance this looks like it's reasonable code, but then it was giving us unexpected outputs. So let's take a look at this code in action. So I'm going to change to lecture 10 here. This is where I got this code. This code is called longstring.c. So let's take a look at it here. Longstring.c is just that code. It's really nothing special. But let's split my terminal and we'll change to that directory, and I want to run it. So clang wall longstring.c-o longstring. And once it compiles, I'm going to run it, and I'm going to pause here for just 3 seconds. Think about what you think the output is going to be. These square brackets that I have over here on the printf are just so that we can see each character in isolation by itself. Okay, I'm going to run it. That does not look like what I thought it was going to look like when I started thinking about this code. And when the student that I was working with was looking at this code, it's not what they thought it was going to look like. The assumption that we have here in the code that we're looking at is that the value of I, so in the loop itself, the value of I here, the assumption that we're making is that the value of I never goes past the length of the string that we see here. But in the code that's been written, what we have is the loop terminator. So the end condition of this loop is I is less than line length. Line length is 80, so it's just going to keep on going past. This is the place where we're violating the assumption that we have that the value that we've got is staying within the bounds of an array. We have a lot of implicit assumptions about the state of inputs that we have in our code. We have assumptions like the arguments that are provided to us are not null. A variable's value can never be negative. Indexes are within the bounds of an array. A counter actually reflects the contents of an object. And assumptions are often of the form, of course that's true. And you're going to say this a lot as you're starting to think about the assumptions that you've got related to the state of your code. Of course that's true. Of course it's true that me, would never pass null to a function. Of course it's true that I would never pass a value that's negative to the function that I have written to access an element within an array. Of course that's true. As obvious as it may seem, we as programmers, as computer scientists, we need to explicitly state these assumptions that we have about the code so that when other people are using our code and when we are using our code, we know what the assumptions are and that we know that we are going to enforce the assumptions that we're stating in the code that we've got. So let's think about now taking these ideas of assumptions that we've got. We've listed a bunch of assumptions related to the inputs. We've listed some assumptions related to the outputs. Let's think about how we would implement design by contract. Design by contract here again is we've got these assumptions that we've made about the code that we've got, the state of the code that we've got. So how do we implement that? We can use this function called assert to implement the assumptions that we've got. And this is something that you've actually seen before, like I said, in assignment 1. An assertion here is going to be of the form assert with some logical expression here. So this is going to be something like a relational operator, like greater than. We get these assertions from this assert.h library. assert is a function that really just tests for truthiness, so something that returns a non-zero value. If the expression is true, then code just continues to execute as though nothing happened. If the expression is false, then code is going to stop. And the way that code stops here is that it's going to print out that on line whatever of the file that we've got where that assertion is, the assertion that was written has failed. This is a much nicer error message than segmentation fault. This is a much nicer error message than just continuing past that array index out of bounds and not stopping. In Java, we had that nice feature that we could put a message in the assertion, but in C, all we've really got is the ability to evaluate a Boolean or logical expression and then stop execution if that expression is false. Let's go through and start writing some preconditions and postconditions. So let's start implementing design by contract with assert. A precondition is one or more well-defined conditions that must be met before execution starts in a block, so a function or some other block. This is going to be a check on the inputs that were given to some function, block, or concept, and we're checking that they meet certain conditions. So let's implement some preconditions in makeString. So I'm going to pop open our code here. And what I want to take a look at is strings.c. So strings.c is the code that we've been writing for working with string functions or with strings in C. makeString as a function has a few different preconditions. The preconditions that we've got are going to be about the inputs that we have. I would like to start writing these preconditions with assert.h. So I'm going to include assert.h, and I'm going to start actually writing these preconditions into my code. The assumptions that we had about the inputs for this function were that 1, characters, does not equal null. Characters can equal null. Characters is declared as an array here. Arrays are addresses, but when we've got this declared in a function, an array can effectively be a pointer. They're effectively the same thing. So I want to make this assertion. I'm assuming that you are not going to call, calling makeString with null written in it here. That's ultimately what I'm trying to do. I want to assume that you are going to call makeString and that you're not going to pass a negative value for numchars. I'm assuming that you're not calling makeString with whatever and -1. So assert numchars is greater than or equal to 0. I am also assuming that you're calling makeString with a valid string. A valid C string here is going to be that the last character of the string that you pass to me should be the null byte. So I'm going to say assert characters at numchars is equal to the null byte. I'm assuming that the very last thing in this string is a null byte. These are the preconditions for this function. We stated some of these in the comments that we wrote in the header for this file, but now we're starting to enforce these with assertions. Switch back to our slides. Postconditions, so this is going to be assumptions that we have about the outputs or the end of a block. These are one or more well-defined conditions that must be met after execution. This may be similar to the list of preconditions, but these are going to be applied to the output variables that we've got. So we might have very, very similar things that we're making assumptions about, but they're going to be about the output variables. Yeah, sorry, these verify that the outputs of a function block or concept are meeting certain conditions. So let's implement some postconditions for char at. This is another function that we've got in this string library. So I'm going to go down to char at. Char at itself is a pretty simple function. There's not really a lot that's going on here. Some of the output conditions that we have for this are that, first of all, we are returning a character that's inside the string. So I'm going to check out oh no, I've forgotten the name of this function. Stir-chur, that's what it's called. Stir-chur is a function that will locate a character in a string. I want to use this to find the character in the string that we've got and to tell us that it is in the string that we're looking through. So the assumption that we've got here is the character that we're returning is in the string, or we're returning the null byte if the initial input assumptions were violated. So the way that this is going to look is that we're going to say assert that the character is in the string if the initial input assumptions that we've been provided have not been violated. So I'm going to assert that index is greater than or equal to 0 and index is less than string.length. And so this is the first one. All of these things must be true. Stir-chur, and what I need to pass to stir-chur is the string that I want to look through. So this is going to be string.characters. The second argument is the character that I want to check for. So char at index is what we populated. And what I want to make sure is that this is not equal to null. So here in our manual page, what it says is that this returns a pointer to the matched character or null if the character is not found. So this is the first part. I'm going to wrap this whole thing up in some parentheses. Or the other option is that the input assumptions were violated. So index is less than 0 or index is greater than string.length. That's our first input assumption. That's our first output assumption. So that we have a character that's in the string. The other assumption that we've got is related to us not making changes to the string in this function. The way that we're going to validate that is by making a copy of the string before we start doing anything, and then validating that the string is equal to what that copy was after this function has executed. So this is going to look a little bit strange. I'm going to make a new character array. So this is going to be called char copy of string. I'm going to start using some snake casing here at index. I'm going to say char copy of string, and then we've got this max string length defined in the string struct itself, and I'm going to initialize this to 0. Then what I'm going to do is check that we're not making changes to the length of the string. So I'm going to say int original length, and I'm going to say that this is equal to the string that's been passed to us, dot length. And then I need to copy into the buffer here. So this is the buffer that I've got, copy of string. I need to copy into the buffer the original contents of the string. So I'm going to say strn copy. I'm going to check the manual page for this because I can never remember. Strn copy. The target is on the left side is the first argument that we pass to it. So copy of string. I want to pass to this string.characters, and the number of bytes that I want to put into this, or the number of characters that I want to put into this, is original length. It's the same as string.length. Okay, so we are making a copy of the string here, and we're copying the original string length. The other output assumption then that I have is to assert that original length is still equal to string.length. So the length of the string hasn't changed. And the other thing is that I want to assert that we've got equal strings. I'm going to use another function here called strcmp, and what I want to check is that these two strings, when I compare them, are equal to each other. So I'm going to say strcmp. I'll say strncmp. I want to pass the length of the string that I've got here. I want to assert that copy of string and string.characters for string.length or original length. Either is the same, they're equal to each other. I want to check that this is equal to 0. 0 here assumes that these two things are equal. This is kind of a lot. This seems like kind of a lot to do. This also seems like kind of a lot to do to really just ultimately say string.characters at index. That's what I want to return. That's fair. That's a fair assessment. This is a lot to do. This is also kind of expensive for us to do. And so one thing that I want to add to this right now is I really don't want to make copies of this string if we're not enforcing design by contract. Design by contract is something that we can turn on and off as we are compiling our code. And we will see this a little bit later. But the way that I can turn it on and off as we are compiling our code is to use a preprocessor directive. The preprocessor directive that I want to use here is called if-and-def. This is literally a conditional statement, and it's saying if not defined. If not defined, ndebug. Assertions can be expensive. So all these assert statements that I've got can be expensive. This searcher is a linear search. It is an expensive operation. I can turn assumptions and assertions off by passing a special compiler flag, and it's called ndebug. I can also make entire sections of code not be compiled or not be included. So in our preprocessor, what we've seen so far is that it will copy and paste things, or it will insert entire contents of files, but we can also make sure that it doesn't include anything. So here I'm going to say if ndef, ndebug, and ndif. This is only going to be here if assertions or designed by contract are turned on at compile time. This is only going to be there if this ndebug is not defined. I also then need to make sure that these are wrapped into this, although they are not going to be there anyway, but it's not going to hurt. So if ndebug, if ndef, ndebug, ndif. Okay. So here we have a post condition defined for this, that the the string itself has not been modified by this code. All right, great. So that's our post condition. Let's switch back to our slides here. The other part of design by contract, so we've got preconditions and post conditions. The other part of design by contract is invariants. If you look up the word invariants on Google or other search engines, you're going to find different kinds of invariants, and we're really specifically focusing on class or type invariants. Class or type invariants are validating ultimately that an object or data meets certain conditions during the execution of our code. And this is the state of an object. The state of an object is going to be the properties that we've got are going to have values that actually make sense for what we're looking at in terms of this thing. This is usually implemented as a function in your code that you call as part of the preconditions or postconditions that you're defining. Let's make an invariant for our string structure. So let's head back to our strings.c code here. And what I would like to begin doing is to define an invariant for a string. I'm going to write a new function here. It has a void return type. I'm going to call it checkString. And what I'm going to accept as input here is an instance of a string struct. This is a void return type because it doesn't need to return anything. We're going to be filling this with a bunch of asserts. If any of the asserts fail, then the function is going to stop executing. We're going to print out this error and then our code is just going to stop. Having it return something isn't really necessary. If the code stops executing, returning something doesn't really make a lot of sense. So we don't need to return anything here. In terms of our string structure, we can see our properties right here. They're right there beside us. A valid string has a length that is greater than 0, greater than or equal to 0, and is less than max string length. A valid string has a null byte \0 at the last character, at the length of the string. We could also say that a valid string has length equal to the number of characters counted before the null byte. So we can make this assumption that a valid string has a null byte at the length of the string, but that doesn't say that there's going to be null bytes. This doesn't say that there's not going to be null bytes before that. So we could go through the process of counting this up. In this lecture, I really just want to take a look at these first two. So to check a string here, I'm going to say assert that the strings, first of all, I'm going to say assert that s does not equal null. I need to make some assumptions even in the invariant that I've got here. So assert that s does not equal null. I want to assert that s at s length is greater than or equal to 0, and s length is less than max string length. And I want to assert that at s characters, s length is the null byte. An exercise for the reader here now, that's you. Implement checking if the number of characters before the null byte is equal to length. The way that you do this should also be wrapped around with that if, endef, and debug. We don't really want to do that at runtime when we're giving this out to our parents because it's going to take a long time every time you are calling this checkString function. Check string is something that you could be calling, for example, in your make string function. So I'm going to put a call to check string right down here. I'm going to say that when I return a string to you, that this string that I'm returning to you is valid. It is a valid string that I'm giving back to you. This is a post condition of this function. A post condition of this function is that the invariant for the object that we are passing back to you is true. This is something that's true. All right, so that's it. That's design by contract. You should now be able to define the pre and post conditions for a routine. You should be able to define invariants that encapsulate the valid state of an ADT. And you should be able to use preconditions, postconditions, and invariants to validate the runtime behavior of an ADT used in an application. We will revisit this in class. We'll spend some time taking a look at a couple more examples. I'll spend some time asking you questions about what you think invariants, preconditions, and postconditions should be for some more code that we're going to be writing. We'll do maybe a tiny quiz on this, but I want to make sure that you have an opportunity to ask me some questions about this as well. That's it. Thank you all for paying attention to this extra little lecture, and I hope that you have a great day. Bye, everyone.